Oh, I forgot to start recording the video. We can see that there's pound sign here is number 35, and exclamation is actually right above it. It's 33. So if we have a 35 and a 33 together, it goes pound and then the other one, 33. Okay, that's our number. This is going to be multiplied by 256 because that's the ones place. That's the 256s here. Looking at this, and this is a 8-bit value here. Okay, so we can calculate the magic number easy enough from that. I won't bother. Okay, so that's the number you can put at the beginning of the file. That's kind of a handy magic number because it's easy to put at the beginning of the file. So if I look at this program here, Pyramids, it's a Python program. And as it happens, a Python comment is very conveniently a pound sign. And if I try and run this thing, that's not auto-completing here. It's going to give me a permissions denied. That's because we don't have execute permission on it. We can fix that. Okay, now we've got execute permission. We try and run it, and gives us some errors here. Basically, it didn't know what to do with it, and it tried to do something with it, but it wasn't the right thing. Okay, let's use our let's take a look at this thing with file. So, file can actually recognize it as a Python script. It might be using the extension, it might not be. Let's see. Nope, figures it out. Okay, so file is actually looking at this thing and figuring out what it is, which is kind of cool. I'm not sure exactly what it's keying that determination off of, but it seems to be figuring it out somehow. Okay, the shell on the other hand is not. If I try and run Pyramids, it is not working. Okay, so the symbol up here means that what follows for the rest of the line is a program to run this file with. Okay. So it's a magic number that will let the operating system go ahead and look at this and be like, okay, this is some kind of script, and then follow the rest of it to figure out what do you do with this type of script. Okay, so I put that there, and now it runs. It draws pyramids. Cool, huh? Anyway, so that's magic numbers in files. Okay, other files will have magic numbers at the beginning too, JPEG or image or PNG image or whatever. And so that's how the operating system can tell what kind of file it's dealing with. Well, shell can anyway. It's not really kernel level there, so I ought to mention it. Okay, permissions and execution, that's really more of a CS228 issue, but just a refresher here. If I do ls-l on Pyramids, you can see it's the permissions here. This is the owner of the file. This is the group of the owner. This is all the rest of the users. And so you can see we gave execute permission to each different group here. And that determines whether or not a file can be executed. So if I say /pyramids, I can just go ahead and run this thing. If I change these, and ls-l again here, let's just do the right one. You'll see I just took away execute permission from everybody, and it will no longer run it. Okay, and you notice it's also not colored green over here. ls, when you color things, it'll make directories green, and it'll make make executables green, directories blue, and it's got some other colors, but they're less common. Okay, let's go back to the mounting. Did I talk about mounting yet? I don't think I talked about mounting. I think I might have. I would have mentioned it in Linux class, so you guys probably remember like what the term means, maybe. Usually in Linux class, I explain it. It's like if you have a deer and you want to integrate it into your house, you might stuff the head and attach it to your wall. And at that point, that's the location it is mounted. And you can do whatever you like with it at that point. You can also mount the entire beast. I used to work in a microscope lab regularly where it's just outside this kind of like museum where they had all these mounted animals completely. And they had like big ones and small ones. They had like moose and wolf and whole, just about every type of duck. And it's pretty cool. Okay, So the file system is the same way. You just take it and you integrate it in your file system at some particular point. So let me make a directory here. I'll call it mount point because that's what it's about to be. I'm going to use it as a mount point. And so since I just created this directory, it's empty as you can see. So we'll go ahead and mount some files there. We'll take a file system and we'll stick it right here at that point. There's probably some file systems on here I could use. So let's see, we have dev SDA3 there. That's where our root file system for Linux on here is. And my guess is there's going to be a dev SDA1 and SD everything. That's impossible to see. I want to get rid of the color. There we go. I can read that. Okay. Actually, that wasn't that bad on the projector. It's harder to read on that screen. That's weird. Okay. So I got dev SDA 1, 2, 3, and 4. And so let's take a look at the partition scheme on this thing. Okay. Sudo for this. cfdisk/dev SDA. cfdisk is a partition manager. And so if we do this, and I remember that my password is worm on this system, and not any of my regular ones. Okay, so you can see what the partitions are here. SDA1 is an NTFS partition. It's system reserved. I don't know what we're doing with that. It's only 104 megabytes. SDA2 is also an NTFS partition. NTFS is used for Windows, so that's going to be the Windows partition from this machine. And then SDA3 is the ext4. That's our Linux file system, and then we have a swap file system. So let's go ahead and see if we can mount one. SDA2. Let's go for SDA2. SDA1 had hardly anything in it. At our mount point. Okay, so now we can see all of the Windows files. You might notice that some of these things are highlighted green. Highlighted green means it has permissions. It's a directory with permissions 777, basically. NTFS doesn't support partitions the same, or permissions the same way that Unix file system would. And so you can see all of these have execute permission. In fact, if we look at this with ls-l, we have full permission on every single file in here. Windows NT did introduce a permission scheme, but from the Unix side, we don't know anything about those permissions. And so they're all coming out as 777. Okay. Okay, I turned off my colors for a minute on LS here, because otherwise it's going to be hard to see where we're going. So now we've got the, what we've done is in our file tree, slash is the root of everything, and then we've got home, and then we've got my directory here, and then we've got this thing, mount point. And inside this thing, what we have is drive C, basically. And you might also notice that we have full access to drive C on here. And if you go to, say, Windows, for example, there actually isn't any particular restriction on what we can do. So I find something that's like totally benign, so I can show you I can change things without damaging anything. Because otherwise somebody will have to fix that. There's notepad.exe. We could move it. Is there solitaire in here? No.
No, you can grab sol with the asterisk after it.
Yeah, well, it'll find it even as there. I think these actually don't have solitaire on it. Here's the Windows initialization stuff. Let's not change that. Can't believe I don't know Windows well enough to figure out a benign change I can make inside the system directory and not damage anything. I can change write into Notepad and vice versa. Nah, that's all just silly. Okay, well, if I did this, it would really mess up Windows on this system. We don't want to do that. Okay, but we got full write access here. And so if I knew what I was doing, I could go change stuff on Windows to undo the deep freeze or give us better permissions or that kind of stuff. In fact, on my security class, I forgot about it last time I taught it. the first time I taught it, we covered how do you change the password on a Windows machine, assuming you forgot the password. And basically use a Linux boot disk and boot up and mount the file system, and then use a utility to go change what the password is in it. We didn't get changing the password to work. We only got blanking the password to work, like remove the password. And then you got to boot up in Windows and set a password if you wanted a different one. But we did get in just fine. That worked good. So anyway, we forgot that. I forgot that the last time I taught security. I got to remember that the next time, because everybody enjoyed that. They thought it was fun. Okay. And so if you had a security class and you're feeling like you really missed out now, just look online for like password reset disk Windows, and you'll find them out there. It's a simple procedure. You can figure it out on your own. Okay. So you can mount this stuff. Okay. Let's unmount it. Actually, I changed my mind. Let's go to desktop. We go to users. Student, we should have desktop, if I can put my fingers in the right place. And we got a bunch of stuff here. Okay. Document.txt. Okay. I made a change. You can see if we can do it now. I'm not going to reboot into Windows just to see it, because that'll take like half the class for this silly thing to start up. But maybe we'll start with Windows and show you there next time or something. Okay. Okay. So what was I doing next? Oh yeah. I wanted to show you that there's that's mounting a file system. Like that's kind of the normal way to do this stuff. There's also a program out there called SSHFS, which will let you mount a file system over SSH. So, by SSH into iSoftera, I have remote access here. So, SSHFS, iSoftera, all my files there at mount point. That's for my password. Okay, so now what I've mounted here, instead of drive C, is my home directory on iSoftera. There we go. So that's how the file tree looks now. And if I do df-h, I should have done this before. Df-h gives me a summary of the file systems I have. -H stands for human readable. It basically puts units on these size columns here. So you can see I've mounted a 5.5 terabyte file system at home Seth mount point. And that's coming from iSoftera. And the latency on it is, it's going to be there certainly, but it's not very big. Primefinder.c. It pops up pretty quick. I think this is a demo I did in some class. Talking about multi-threading. I don't even remember what class. So anyway, you can just go ahead and use it like the files were right here on the instructor machine. So I think that's kind of cool. There's another file system called Network File System, NFS, that's more commonly used for this kind of stuff on a wide scale. On a small scale, SSHFS is great because the computer that you take the files from only has to be running SSH and that's it, nothing else. And so you don't need to set up a network file server on it. A lot of times in a lab installation like this is how it was at both universities I worked at. When you sit down on a machine and log in, /home on it is actually going to be coming from a network file server somewhere. So you actually sit down at it and log in with your username and password, and then /home is the same across all the machines in the whole lab. And so your files are the same across all of them. And that's kind of handy because it doesn't matter where you sit then in terms of whether you still got your file or not. One other cool thing about it is if you log into multiple machines at the same time, you have the same files on all of them. And so some of us there are playing around with distributed computing. You could log into those workstations remotely. They were all running Linux and had SSH open. And so you can actually do like a distributed computing project in the lab by making a script that goes and logs into a few of them. And actually, near the end of the networks class, we did a demo where we set up distributed computing in this lab using that, although it didn't, it kind of worked. It worked. It just didn't have all that many features. Okay, so that's SSHFS. So, Have I mentioned the term daemons yet? I can't believe I got this far in operating systems class, so I'm mentioning it. As a background process. And so in Unix, anything that runs in the background is called a daemon. And so a lot of this stuff in here is a daemon, like Pulse Audio here. It's an audio daemon. The reason it's consuming some CPU usage is when I talk, it's going into that microphone up there, which is getting processed by the Pulse Audio sound system, which is involving its daemon, and then getting recorded. Going back to this program called Cheese. Okay. So daemon is just a process that runs in the background. It's got this extra A in it, and so I've heard it said daemons most often. Sometimes people call them demons, especially if their computer is not working right or is acting funny. So anyway, that's an auto-mount daemon. It watches your computer, and then when you put in like a CD or a USB drive or something like that, it'll automatically go ahead and mount it. And then you can go ahead and use it, which is how people expect computers to work because Windows runs an auto-mount daemon. In fact, Windows not only runs an auto-mount daemon, it'll actually automatically run a program on a CD, unless you change the settings so it doesn't. And so when you put in a CD in a drive, it looks for something called autorun.bat, if I remember right. And that's a bash script, a Windows script. And it'll go ahead and run that. And so for a while, Sony was distributing music CDs that had a rootkit installed. So you put the CD in, and it would automatically run the rootkit, which would install software in your kernel to make sure you didn't copy the CD. But it turned out it actually had a security vulnerability, and they kind of got in trouble for it. Anyway, so the auto-mount daemon just looks for something that's added to the computer and automatically mounts it. Oh, mounting in multiple places. Hey, we can do that. Okay, let's let me mount this thing again. Okay, so if I look at my file systems here, slash on this system is devsta3, and that's just mounted at slash. Where else would it be? Well, the answer is it's going to be mounted at mount point. Okay, so now if I look at df-h here, where's mount point? Everything's mounted there. It's not showing up in df-h for some reason, and I'm not sure why df doesn't seem to recognize it. Whenever I mount, it'll show me a list of things that are mounted, and this actually does show it there. df is actually for assessing your disk usage, and so maybe they put something in there to not include redundant entries. Oh, anyway, you can see devsta3 is mounted on slash, and it's mounted at home Seth mount point. Okay. So if I go into mount point here, I got all my stuff. I go to dev. Whoa, it's actually populating. Proc isn't. Oh, and dev isn't fully populated either, like the drives aren't there, for example. So the fake files didn't necessarily all make it over. But if I go to, say, home on here, and Seth, oh, here's my files again. And if I go to mount point, they're not here. So when you mount something, it gets mounted at a particular point in the file system. And so it's not here is the reason that it's not here. I mean, the files are not actually in mount point. They're just mounted at home Seth mount point. And they're not mounted at home Seth mount point, home Seth mount point. And we could mount them there. But this is going to be a manual thing. Okay, here's something else. Okay, here's instructor stuff. Okay, that's like a new file. No permission here. We didn't change the permissions just because we mounted it somewhere else. The instructor permissions are set fairly permissive, and actually so are mine on here. Basically, anybody can go root around in the home directories via these things. And this is partly so, if I do a class example or something, and you're like, where was that thing? You can just start up this computer to go find it. So they're there. Okay, so yeah, you can totally mount something in two different places. And if I go to mount point, home stuff, and say decide to remove something. Let's remove untitled everything. Okay. It is gone here too, because it's the same file system. Okay, let's show you something else. So here on our software up by df-h, we've got, so that at slash, we've got dev-sda1 mounted, and at slash home, we've got dev-sdb mounted. Let's see if anybody's using this system. One person, okay. Well, he's been around a while. This probably won't kill everything that he's doing right now. This is fine. Plus he's right here, so it's fine. Okay, I'm going to unmount slash home. Oh, it's right. It's busy like for a dozen reasons. Okay, fine. I wanted to unmount slash home to show you what happens, but it's right, and I shouldn't try to force the issue. That's a pretty bad idea. Yeah, so slash home is actually mounted over something called slash home. Let me explain what I mean by mounted over. Okay. Do I want to become root? No, I don't. Okay, I'll just go here, and I'll make a directory called TMP, or my TMP. It's not everybody else's. Okay, so I've got this directory here, and I'll go ahead and put some files in here. I'll copy everything that's a Python file. Oh, is there nothing that was a Python file? Is it, whatever. Okay, there we go. So I got this directory here, TMP, and it's full of stuff. Okay, so now I'm going to go ahead and mount something. Dev SDB, that's home, at TMP. Okay, so now I've got home mounted there. The rest of the files are hidden. We can't really get to them because we mounted something there. They're not gone. They're just kind of hidden. Now they're back. Okay. So when you mount something over something else, you can't access the files that were wherever that was. So the weird thing about home on my software that I was going to show you, but I won't. There's a lot of user directories in slash home that have actually been there for a good while. And when I first set up the server, it had one drive in it, a single 1 terabyte drive. And I wanted to set up a big RAID array, and I didn't really want to redo everything afterwards. I set up a file system on my OneDrive and then set it up on the RAID array later. So I just sort of left the drive alone in front of the machine and started everybody off with just one partition, starting at slash. And so slash home was in the same drive as slash and everything else. Well, when I finally set up the RAID array, there were home directories and things, and so I made my partition, mounted it somewhere, copied over everything from home, and then mounted that over the old slash home. So there's actually old files at slash home that nobody, including myself, can access easily. But they're there, they take up space, not very much space, and they're well hidden. So actually, if you want to hide something on a Unix-style machine, mount something over it. This is the equivalent of sewing all your life savings into a mattress, You'll hide it somewhere and nobody can see it. Okay. So there's that. And I think we'll call that good. We reviewed permissions. Tail.f is really a 228 thing. I got other stuff to talk about today. Such as FSCK, which is File System Consistency Check. So the utility FSCK, I thought I should mention the name because it's unusual and it's unintuitive. Okay, apparently we shouldn't run a file system consistency check right now. So maybe we won't do that. I don't think it would let us anyway because I didn't run into sudo. So I guess you can't check the file system consistency while it's running. Anyway, basically what a file system consistency check does is run through the file system and make sure everything is set up correctly. So, if you got a file allocation table system, go through the table, make sure you got valid entries, make sure each entry actually leads to a file, and that sort of thing. And the FSCK utility has actually got rather more sophisticated and will attempt to fix stuff these days, which is good, I suppose. But it does a lot more than its name might imply. Okay, so that's the gateway to all things involving rebuilding the file system. Let's get back to layer file systems in a minute, if we do. Okay, so talking about file systems again. Now let me see what the operating system does with these things. There's a lot of features that they might or might not have. Journaling in a file system, it tries to avoid this issue. Suppose you've got a file system and you're saving a big file on it, and halfway through saving the file, the power goes out. That could be a problem, because then you've got this half-written file. And so when you start the computer up again, there has to be some way to assess, well, how much of this file actually got written, what do we need to do to redo it, and how are we going to recover from this mess. And so anyway, the file system consistency, or the journaling, before writing something to the disk, the file system actually writes a record of what it's about to do, and then it does it, and then it marks on the journal that it actually was finished. So then when the computer starts up again after the power's gone out, you can see, well, we were going to be writing this file, and there's no mark that it was finished, so there must be a half-written file here. And then it can be removed or whatever. And so journaling is actually pretty good in terms of recovering a file system quickly from some kind of power outage. Most file systems these days support journaling. Journaling wasn't a universal feature 20 years ago. In fact, it didn't become standard on Linux installations really until, I guess, about 2000 or so. But these days you usually see it. Now, the downside of journaling is if you're going to write a file, you've got to write that you're going to write the file, then actually do it, then write that it was done. And so there's a little bit more writing here involved, and so it slows file systems down. For a long time, I used to run ext2 instead of ext3. The improvement in ext3 was that journaling was added, and I didn't particularly want the improvement because it would make the computer slower. And that was something we really cared about back then. Okay, so journaling's out there. Most people use it these days. All of my systems use journaling file systems these days. B-trees. I talked about B-trees already, so that's why I kind of did that. Most file systems use some kind of tree-like structure these days, and B-trees are the most popular. There's different forms of B-trees. I forget the exact difference between a B- and a B+ tree, but B-trees are typically used. Major point of a B-tree, like I was explaining earlier, is you have a whole bunch of entries in a node, so you can read the whole node at once. Support for parallel operations is it's something that is usually featured these days, because most of the time these days you might be running multiple processors, in which case you might access the file system multiple times at the same time. And so the file system needs to be okay with that. And they're generally all okay with it. The question is, how exactly do they handle the situation? See, one way to be okay with multiple processors and users is to just say, well, only one person can read a file at once. And so if somebody's reading a file and somebody else tries to, we'll just go ahead and queue that up. And it makes a tremendous amount of sense if you have a mechanical hard drive and can only read one thing at once. But it makes a little bit less sense if you got a user who is accessing little bits of a file and wants to leave the silly thing open. Open in the sense of we're going to do a sequential read through the entire thing. You might want to sneak in another request partway through. And XFS is pretty good in terms of multiple user support. For the most part, it doesn't actually matter that much because your drive can't multi-thread. And so if you just have your file system make the next user wait, that's mostly okay. It's just that if one user has decided that what they want to do is copy an entire DVD, it might be nice if you could sneak somebody else in partway through. Okay, so parallel support varies. And, okay, yeah, it just does. Okay, expansion. So one thing that, this didn't used to be expected of a file system at all, but it kind of is now. So suppose you have a hard drive, and you also have a RAID controller in your computer. And after a while, you decide your hard drive is too small, and you want to add another one, and you want to stretch your hard drive, your file system, over both hard drives. For the most part, they'll play ball with that these days. And the other place you see this situation is in partition management. So I showed you a moment ago the partition table on this one. SDA. Okay, and you can see we got these 4 different partitions. Well, I think I ran this with sudo and things. I shouldn't hit delete even if I don't intend to write the changes to the partition table. If I was to say, you know, we're not going to use Windows anymore in this system, it's going to be a Linux system, it would be real tempting to go ahead and delete these 2 partitions. And then it might be nice to take this partition and expand it to be that full size. Well, that's something that most file systems will support these days, but they never used to. And you can see how this would be a complicated deal to take care of, because if you got some sort of area and disk reserved to keep track of where files are, all of a sudden you got space that's not part of that anymore, and it needs to account for that. On a file allocation table style system, a lot of times it's just plain not supported, because there's some table that says where all the files are, and that table's a certain size, and you can't make it bigger without moving everything it would run into. It's not an insurmountable problem. You know, you could say, well, at the very least, you could take the table and mark that it went somewhere else and write it into some of the new area. A little bit more difficult is the idea of contracting the size. You know, I'll say, okay, we're actually going to make that SDA4 a little bigger. We're going to make it 8 gigabytes, so we're going to take 4 gigabytes off of SDA3. And that's something that file systems do actually support. They have to relocate all the files that are in that extra part. And of course, there does have to be enough extra space, or it's just plain not going to work. Okay. So anyway, that's an active issue out there. Aging is a funny thing. So this is kind of the thing where, you know, if you get like a new dresser or something, you know, you use all the drawers and they each have their own purpose. And then a year later, the drawers have kind of lost their purpose and everything's all mixed up. And all of a sudden, you're actually storing motherboards in what used to be the sock drawer, and the socks are half stuffed under the shirts and that kind of thing. That's file system aging. Like, it used to be organized, and now it's not. And file systems do this to some extent. Think about the file allocation table system and the defrag. What the defrag does is roll back the clock on the age of the file system. Basically, things have been written and erased, and new things written, and all the files are broke up into little pieces. And so you need some kind of utility to undo the aging. In a B-tree file system, you end up with aging too, because if you have some kind of a B-tree, and it follows some sort of pattern here where you got some entries and then some kind of other nodes, each with their spots, and so on. You might end up with more nodes than you need at certain points. You can end up with a tall tree because it had a lot of files, and then some of them got deleted, and it doesn't need to be that big, but it still is because it was made that way. And so you can end up with the same kind of thing, where it's less organized than it was right at the very beginning. In some cases, RiserFS is criticized for doing some aging. Okay, so aging is an issue out there, and so in general, when a file system is designed, the file system designers need to come up with some kind of mechanism to undo aging or to deal with aging. Bring it back to age 0. Maximum file sizes. Let me show you. These actually vary a bit. Okay, let's start with FAT32. So if we look at this, we'll have some kind of a table of limits here. It looks like max volume size. FAT12 can go up to 32 megabytes, which is not very big anymore. But FAT32 here can go up to 2 terabytes, depending on what size sectors you have, which is big. Max file size, though, is a little bit smaller. You can have a maximum file size of 4 gigabytes, and that's as big as it goes. And that actually is getting to the point where it can be a problem if you got a video camera and you just went out and bought a 128 gigabyte SD card, and you put it in your video camera, and you're like, okay, well, this is great. I'm going to go make an hour-long movie. The file is probably bigger than 4 gigabytes. And so you have to break them up. Yeah?
I have a problem with a game called Borderlands 2, where it wouldn't load on a FAT32 because one of the files was bigger than 4 gigs.
Okay.
Yeah, I had a video file I downloaded at one point that was like, I think it was like 4.7 or something like that, and yeah.
Yeah.
It was a pain to transfer that around.
Yeah. Yeah, because it won't go onto a memory card or USB stick or a lot of other
Yeah,
stuff.
unless you split it up or reformat.
Yeah, yeah. Some people run a file system other than FAT32 on memory sticks in order to get around the issue. The only thing is, if you're like, okay, well, I'm cool, I got XFS installed on my memory stick, it's not going to work if you go plug it into your friend's computer. It will if they run Linux, but you know, they probably don't. So.
What is UFS? Have you ever seen that, like on a thumb drive or something? It says that
No.
it's formatted with UFS.
I haven't. What is UFS? Good question.
Universal flash storage.
Or Unix file system.
I don't know.
Oh, and flash storage
Uh,
specification. That doesn't look like a file system now.
It's a Unix file system.
Well, yeah, there's also one called Unix file system, but I doubt it's putting that on there.
Yeah.
This is older file system, but it apparently is well supported still.
Nokia.
I haven't actually heard of anybody using UFS. You can see it's a descendant of the file system used for version 7 Unix, so it goes back a long way. Actually, its maximum file size is pretty good. 8 zettabytes, zebibytes. I don't know what a zebibyte is. It's more than an exabyte, which is more than a petabyte. So you won't run into your 4 gigabyte file problem if you actually have one that's formatted with Unix file system.
That's ridiculously large.
So yeah, it's okay. So FAT32 has these limitations. Probably on a modern Windows system, you're going to use NTFS, which was introduced back in '93, and so you can see the max file size is fixed. UFS actually had a much bigger max file size. I mean, this one, 16 exabytes, up to, well, okay, it depends a little bit. But it's pretty big regardless. And a max volume size, you can see there, it looks like is 256 terabytes, which is beyond the range of hard drives right now. Hard drives these days go up to about 8 or 10 or something like that. But if you put enough of them together, you could actually get up that high. But NTFS is used for high performance computing anyway, and so it's highly unlikely to end up on with that big a file or that big a file system. I use XFS for a lot of machines. There's Silicon Graphics put this one together back in '93, they've worked on it a long time since then. It actually works pretty good. It's a B-tree-based file system, and where's the limits? Okay, max volume size 16 exabytes, max file size 8 exabytes. And exabytes are way beyond what our drives are these days, and so it's pretty future-proof at the moment. Eventually we'll get there. I mean, with FAT30, you saw with FAT12 had a maximum file system size of 32 megabytes. Yeah, when it came up with that, it was huge. And so this is too. JFS is a journaling file system. This is something IBM uses, and it was named because it journals. And B-tree again, and 32 petabytes and 4 petabytes, and so it's actually quite a lot lower. Oh, the other thing you can run into is max number of files here. This one doesn't really have any defined limit on how many files you can have. It can keep expanding its B-tree as far as you want, and that's reasonably common these days. XFS, for example, here, does it even say max number of files? Probably not. I don't know, okay, it doesn't say. Most of them don't have a particular limit, but if we go back to FAT32, it might. Max number of files, FAT32. You can have 268 million files, and that's it. No more. It's going to be a file allocation table size problem. So there's limits to these things. ext2 was the standard for a long time on Linux. ext1 I don't believe lived very long. And so anyway, ext2 introduced with Linux. 2 to 32 terabytes, which is actually where we're getting to. People don't really use ext too much anymore. Max file size, 16 gigabytes to 2 terabytes. This depends on cluster size of both of these. Remember, I drew the little pigeonhole things, talking about little shoe holes or whatever. Depends how big you make those things. Because the limits that you run into here are, it's probably going to be integer sizes or something. But you run into a limit on the number of holes you can have. And so if you make them bigger, you can have more space. So anyway, that's ext2. These days, people, if they're going to use an ext family file system, will use ext4. ext4 it uses a linked list and it does have this hashed B tree, but it has the distinction of being probably the least reliant on B trees of any of the current file systems. I don't know if that's a good thing or bad thing. Normally it's considered a bad thing, actually. But anyway, so in terms of limits here, they're higher. Max volume size, 1 exabyte, or, possibly, I don't know. It's got a max file size here, 16 terabytes. Oh, and this one actually has a maximum of files at 4 billion. Okay, ZFS is FreeBSD's file system. Well, it's the one FreeBSD uses, I guess. Looks like it actually came with Solaris. But anyway, fairly high limits again. And say that the B-tree one, I believe it is. I don't see it saying anything. Okay, so they got vastly different limits in terms of what they can support. I didn't go look up what everybody with Max is using. I guess I probably should. I'm not sure which one they even use. ZFS, is that what they're using? No, it came up. Oh, I don't know. You don't need to watch me read Wikipedia. You can find out yourself if you really want to know. Okay, so another note on here. So the journaling and things, it's nice to have something that can be recovered, but nothing protects you completely if your drive fails. The usual stated measure here in terms of hard drive reliability is to use RAID. Stands for Redundant Array of Inexpensive Disks, normally. There's a few other things that it's sometimes stated to stand for. I think that's the most common. Anyway, basic idea with RAID. So suppose you have a computer and you have 2 hard drives in it, and you want to have some kind of advantage in terms of reliability. You can just say, okay, these 2 drives are going to be exactly the same, and so when we take some kind of file and we write it into this thing, we'll write it in this one, and we'll write it in this one. And so then, if either of these are lost, we've still got our file. Disadvantage here. It can potentially take slightly longer to write. Not very much. You can write to both of them at the same time. And so whichever one finishes last is how long it took. And they might be in different points on their cycle and whatnot, because they're spinning, and one of them might get to a little bit faster. But in general, this is not really going to slow things down a lot over one hard drive. Reading things back, it actually can help. The reason is, if you're going to read this file back, you can read the first part off of one drive and the second part off of the other drive at the same time, which is pretty cool. Goes a lot faster, right? So that's kind of neat. So you can actually boost your performance to theoretically double the bandwidth. You are going to have to wait for both drives to find their spot, and so whichever one finishes last is the one that kind of dictates how long this thing took. But it's still better. It's faster there. One disadvantage is you had to buy a second hard drive, and you don't get to store any more files because you're copying them on both of these. Okay, this is called RAID 1. Okay, RAID 0. Probably this above it. RAID 0, you take the file, but instead of writing it on both drives at the same time, you write part of it on one drive and the other part on the other drive. And that way you get just as much space as you'd have with the 2 drives, because they're each storing half as much. And you can write it twice as fast, because they each have to do half as much writing, and you can read from it twice as fast, because you're reading from both of them at once. Those are all great. Here's the problem. If either drive dies, you lose all of your files. So running RAID 0 is a little bit risky. The reason it's called a RAID 0 sometimes, and this is commonly cited, I don't know if it's true, the R stands for redundant, and so this isn't really a RAID level. Anyway, that's what RAID 0 is. What a lot of people run is RAID 5. And there's other RAID levels here too. RAID 5, you're going to need 3 disks. And so you run the file into this thing. And basically what you do, suppose you got a byte of the file. And there's your byte. And so you want to write this to the system. It does a larger increment here than a byte. I'm just trying to explain the concept. Okay, so on one drive you write this. On the next drive you write this. On the other one, you XOR it. And so that gives you a 1, a 1, a 0, and a 1. Okay. So if you think about this for a minute, you can actually get back either of these parts if you have one of these and this one. And so if you lose one drive, you can actually put it back together from the other two with a little bit of math. And so it gives you protection against a single drive failure. You get as much space as 2 drives would have, and of course you bought 3 drives. So that's a little bit of a downer. But you can actually read from multiple drives at once and get high bandwidth. It's kind of beyond the stuff I intend to explain today, but you can actually throw more drives into a RAID array, including odd numbers, and in the case of Isoptera, 7 of them. But they do improve performance a lot. Like on Isoptera, we got spinning type drives for the main storage, and we got a solid state drive for the system. So let's benchmark the solid state drive first. Okay, H2PARM, T2, Dev, SDA. I think it's SDA is the solid state one. Okay, so running a benchmark on here. We're going to get 2 numbers. The first one is cached reads. Those are actually coming out of main memory, and so it's really a main memory benchmark. And it did pretty good. And so here's the ones that are actually coming off of the drive itself. And we got 228 megabytes a second off the solid state drive there. If we look at this one, we got a spinning type drive like the old style magnetic one. This is just kind of a standard desktop drive in the classroom computer here. And I'm betting it'll pull about 100, more or less. The real advantage of a solid state drive isn't throughput. The throughput's higher, but it's how fast you can find a file. And we're not doing like a seek benchmark here, or we'd see some more impressive gains from the solid state drive. But it basically doubled the performance, so that's not too bad. Also, you can see Isoptera's main memory is 5 times as fast as this machine's. So anyway, there's 118 or whatever. Okay. SDB is a RAID array of 7 spinning type drives on Isoptera. And it's got a fancy RAID controller to try to put everything together in good order. Hey, the main memory did a little bit better that time. I just luck of the draw. We got 635 off of it. So that's pretty good for combining together those 7 drives. I mean, if you think about it, 7 drives, it's not 7 times as fast as a single spinning type drive in this machine here, but it's pretty good. I mean, 635 is more than we're seeing on others. I've seen it do better before. I think I've seen close to 800 from it before, but just time of day or whatever. You can see the main memory kind of underachieved on that one relatively. Hey, I got 734 that time. Okay. Depends on which daemons decided to do something right in the middle of my benchmark, basically. If everybody goes and starts hammering on the web server on Isoptera while I run the benchmark, it'll do really bad. Okay, and actually, Isoptera is probably unfairly penalized here. It's running a lot more services than this machine in this room is. Okay, so RAID levels. RAID is good. RAID protects you. Let's talk about Riser FS real quick, and I was going to use it as kind of a more thorough example, but I've only got like 20 minutes left, so we're not going to go over it in that much detail. So I pull up Riser because it's kind of an unusual one. It's always been the strange entry into the race here. One thing that's kind of strange about Riser FS, most file systems, they don't dump like absolutely everything into the B tree. You put the references to files into the B tree, and that's how you find them. Riser, everything on the entire disk is stored in a B tree. The file, all the parts of the file, the directory entries, the metadata, everything. Your entire disk, one B tree. And So, just like picture some beach where you like squirreled away on your whole hard drive, links going everywhere. But it means to find anything on your file system, you're looking at a tree kind of search to get there. So it's not like a tree search to find where the file starts or anything like that. It's a tree search and you get to the actual file. So if you want to seek the file, you just go to the node that explains where everything is on the file, and you can get to the right spot inside the file. So if you have a 4 gigabyte file, it's actually going to get treed. And so that makes seek really super fast. Its claim to fame has always been small files, though. The big file, your write performance is actually going to be hurt a little bit if you have to take the file and turn it into a tree. It's not that bad, but a little bit. Small files are quite easy to find in this because you're doing a tree search regardless. And so the seek time on a Riser FS system has actually usually been pretty good. It supports journaling, supports resizing as you go. It's got this feature called tail packing. So with the clusters, on the disk, you can allocate a minimum of 1 box. And so Riser FS actually has a feature where it can take one of those spots and it basically becomes a node in a tree, and inside it can have more than 1 file. And so you're looking for your file, and it comes down to it's in this node inside the end of the tree. That's great, unless you decide to take some tiny file that got tail packed and start adding to it. And as it grows, the storage solution is going to have to change, which is not ideal because it'll outgrow its node. And actually, if you start growing any of the ones in the tail-packed file, it's going to have to move out whatever you grew, and then it's going to have some extra space to manage at the end of the node. And so that can actually cause a little bit of a performance penalty, but it does save a little bit of space. And so it's a trade-off that's left open to the user. You can turn it on or off if you like. I don't know if you can turn it off after you've been using it, though. Because if you did that, then it would still have to go find stuff into tail packing. The best you might be able to do is tell it don't pack anything more into tails. Okay. It also, one thing that slowed it down a bit. So this was put together back when people had a single processor in a computer. So the number of the processors was 1, and that was the number of the processors. So it used this mechanism called the big kernel lock, which basically lets you stop everything from happening in the kernel except for whatever you're doing until you're done. And you can see how this would be really tempting if you're managing a tree that spans the entire disk. Because if you're going to do some kind of tree manipulation, you're going to take a node far up the tree and split it into multiple pieces. You're going to have to do some housekeeping on this tree. You don't really want to be interrupted halfway through. Because if the user pushes a key and it generates an interrupt, and then the interrupt somehow leads to storing something in the file system while you're working on a tree, that could be very bad. And so anyway, there's a lot of places in it where it was using this big kernel lock. Well, as soon as multiple processors started to be common, the big kernel lock, its days were numbered. It went away pretty quickly. And so Riser FS had to adapt, but for a while there was this problem where you had to compile your kernel with the old support for the big kernel lock if you wanted to use Riser FS. And that was part of what kind of led to its demise. The real thing that led to its demise was lack of maintenance. I think I've mentioned this before. Hans Riser, the guy that put it together, the architect of the whole thing, he killed his wife, who'd come from Russia to marry him. Instantly, her name was Nina. And he hid the body somewhere, and then there was this investigation. And finally, after it was absolutely obvious that he'd killed her because her blood was all over his car and things, he admitted to it and made some kind of deal where he goes to jail for like slightly less time if he shows them where the body is. And so anyway, he's been in jail for a while now. And the parable, strike the shepherd and the flock will scatter. So the project hasn't actually made that much progress while he's been locked up. I guess they figure it wouldn't really be jail if they let him have his computer, because then it'd just be like home. In some ways, it feels like they ought to just make his sentence say, just keep him locked up forever and make him work on his file system. Go write us a file system. That's your sentence for the rest of your life. Anyway, he was working on a successor to it though, Riser 4. This is version 3. And Riser 4 was a dramatic a revision of it. You would have had to reformat to move to Riser 4. And it had all kinds of unique ideas in it, but it didn't quite work right when he went to jail. And nobody wants to use a file system that doesn't quite work right. And so it's never made any traction. Okay. Oh, the old Riser FS. It's still kind of around. Let me show you some benchmarks on file systems. This will kind of show you how much it actually matters. Let's do this differently. There's a number of benchmarks on here, but I wanted the ones on Phoronix because I just looked at the article and they look like they're pretty well done. Okay, it's traditional on any kind of benchmarking article to show you a picture of the computer that the benchmarks were performed on. This is so you can realize that the people that are running the benchmarks are indeed computer nerds. You can tell because they have the motherboard sitting on a box instead of installed in a case. Okay, so credentials established. We can move on to to what they actually discovered. So, job interview trick. If they will ask you for a picture of your computer, just set a motherboard onto a box with some stuff plugged into it. Okay. This is using File System Mark version 3.3. And so apparently they're using 1,001 megabyte files. I don't know what exactly they're doing with it. But whatever they're doing with the files, these bars are in files per second. There's Riser FS. And it didn't actually do very well in this test at all. It did better than NTFS did a little bit. But JFS here was kind of outstanding. This is Turtle File System from IBM. They put this together for mainframes, actually, back in the day. And so this gave it a little bit of a head start, because if you had $1 million to spend on an IBM mainframe, you could have a lot of today's features back in the 80s. And so they had a lot of experience writing a system for a modern system. But that said, that's not really actually why it pulled into the lead here. They mentioned in the caption here that it's syncing less often than the other file systems. So, you know, if you're writing a file system and you want to make it high performance, what you should do is let the users, make a bunch of changes, hold them in main memory until it seems like they're done with what they're doing, and then go right into disk. Like, kind of wait a little while, get everything queued up first. And that does indeed help performance a lot, and that's what it's doing here. The disadvantage, of course, is if the user's busy writing a bunch of files and then power goes out on their computer, they might be irritated if the last few hundred files had only been changed in main memory. But if you paid $1 million for an IBM mainframe, you probably have a battery backup. I mean, it's not going to just have the power go out. So anyway, trade-offs. There's always trade-offs to be made. And did pretty good. Oh, this is NilFS. This did pretty good. This is a more recent one. Okay. NilFS. Current version is version 2. Nippon Telegraph and Telephone Cyberspace Laboratories put it together. It's introduced into Linux, and currently there's read-only support for NetBSD, and it uses a B tree. And this is actually a new entry into the horse race here. And it's no problems with the 2038 problem. I never mentioned the 2038 problem. Someday, not right now. And anyway, it's got a number of OS capability. You can see it's just kind of moving in here. Like Ubuntu 9.10 and later. That's a few versions out of date, but it's coming into here. Okay, so it's a fairly new one, and that's actually the main thing that's limiting its popularity right now. I think is that it's not recent enough that it's not been around long enough. People trust it with their files. Okay, and it's actually noted that it's also syncing a little bit less often. Syncing disk with JFS and NilFS2 is IM. Okay, let's take a look at another benchmark here. So now we see everything kind of changed. They're a lot closer together in whatever they're doing here. They're using 4 threads, writing files at the same time. And so this will actually stress the file system's ability to deal with multiple users trying to access stuff at the same time, which can be kind of important. And NilFS2 actually wins this one by quite a bit, and this is doing pretty good.
Yeah,
Okay.
Windows failed horribly.
Well, yeah, on that one. You know, same kind of story here. Now let's look at the next page. Okay, everything's more or less balanced on whatever they're doing there. Ooh, what happened here? More is better. This is compiled bench, and so they're testing basically a practical performance test here in terms of you know, what would it take to compile something. And all of a sudden, JFS is like practically the lowest. It is the lowest one on here. Whatever access pattern they're dealing with here is not really being very kind to that one. ext4 is actually winning it by a little bit, and XFS and ext3 are doing okay. B3FS isn't that bad. Riser isn't doing very well on that either. Riser's actually not doing very well on this at all. It used to be pretty fast back in the day, but most of the ones that are excelling on here, ext4 is pretty new. XFS has had a lot of work recently. It hasn't stayed static at all. B3FS is pretty new. Don't know what happened to NilFS.
Didn't that Riser guy kill his wife or something, so he's in prison for that?
Yeah, yeah.
Oh. Well, I mean,
Yeah,
you
yes.
probably can't really kill it that easily in prison.
Right, you
You
can't.
could actually
So,
no, you could probably write it on like prison stationery and mail it out.
oh, there you go. They can mail back the results.
Yeah, that'd be fun.
Awesome.
Missing semicolon.
Yeah, yeah. Instead of sneaking in a nail file, I'll be having his relative sneak in a Raspberry Pi or something.
Bake it in a cake.
Yeah, yeah. Be like, oh, it's that's really great, except it's melted. Yeah, just second this transaction performance, yeah. Now we've reversed everything. So here's part of what goes on with these kinds of benchmarks. When you're writing this kind of stuff, different schemes will help in different ways. For large files, for example, finding the file isn't real important. It's the ability to continue reading the file from one place to the next without moving ahead of the drive. That's going to get it off the drive quickly. For small files, the ability to find the file is all that counts. And in fact, in some of these cases, the file systems may have happened to store all the new files together, or they might have spread them out. And on a lot of these tests, you know, they're going to be writing a bunch of files and then reading the same files. Well, if it wrote all the new files together, that's a great advantage. If it merged them into some other, some other kind of search strategy, that's not going to help very much. And so that's part of why we can see these results, be great and completely the opposite way. Most of these benchmark articles are going to come out the same. I thought this one was great because between the second and the third page, it completely flips over for JFS. But most of the time, if you look at any kind of benchmark article, it's kind of all over the map. I don't know how I end up in two tabs, the same thing open. Here's a 6-way file system comparison on Linux 4.1 on a solid state drive. So, we changed the field here. This is like if we were playing football on grass, and now we're playing it on AstroTurf glued to a wall. So, a different team might excel under those circumstances. And there we go, and let's take a look. Okay. ext4 did pretty good. JFS isn't in here. NilFS is, though, and it totally lost whatever benchmark this is. Or more is better. But look at this. Now it's doing great. I don't actually know what F2FS is. Kind of in the pack somewhere and excelling. And a lot of times you seem to see the same couple, excel or not, depending on exactly how the search strategies and that kind of stuff are in here. Yeah, there. NilFS2 is dead last. Dead last again. Not in this one? Not in this one. Anyway, these things just go back and forth and back and forth, and that happens. Okay, hardware benchmarks. You guys are probably familiar with seeing these. If we go to CPU benchmarks, you get the picture. Usually with the CPU benchmarks, they stack up like consistently for the most part, and you'll see little trade-offs from one to the next. You know, it'll be like, okay, this benchmark is a little more favorable than Intel or AMD or whatever, but the file system ones, they are all over the map. Okay, so as far as which one to use, the main thing that people tend to want from their file system is stability. There's very few people out there who are like, this is an exciting new file system that just came out. I'm going to go put all of my data into it. And so you tend to see the momentum behind a file system change really slowly. The other thing is, you don't usually see people change file systems very often. If I go and, so I go over to AMLED here. Okay, DF-H. So, that's not very good. Let's zoom out. Okay. So I've got file systems here that are still using RiserFS because I bought the drive back when RiserFS was a pretty good choice, and back when it wasn't written by criminal, and you know it's on my drive, and I'm not going to reformat it just to change file systems. And so you end up with a lot of you. Oh, here, whoa! I got one on ext2. So I probably formatted this drive, I don't know, 15 years ago, and maybe 10, I don't know, but you know, a while ago, and I haven't changed it. And so this is pretty typical in use of file systems. So new options moving really slow, and when people actually pick one, they tend to pick a fairly solid choice. If we look at mount on here, I've got some XFS systems, file systems on here, and both XFS? No. I've got ext4 as running in the system partition. Yeah, ext4. ext4 is a pretty standard one on files on the Linux. People used to have this kind of saying in IT, nobody ever got fired for buying IBM products, because IBM was kind of the standard choice, and if you did it, it wasn't outlandish. And if you went and bought from some other upstart competitor and it didn't work out, you get fired. Well, that's kind of the way the ext series is in Linux. It's been with the Linux kernel a long time, and people generally trust it. Oh yeah, and finally, if you really want to be a file system nerd, you could go and set up a partition with each of these, and then keep your large files in one and your small files in another. And when you're going to run some program that creates a whole bunch of small files, you don't pick the right file system and use it. Everybody's like, yeah, I'm going to go home and do that. Okay, good. Okay.
Lab 5, no.
Yeah. Okay, we're pretty much out of time. I do want to give you one random note about XFS. It has this unique feature. Real-time operating systems have to guarantee performance in a certain amount of time. It actually has a feature where it can guarantee a certain amount of bandwidth if it's reserved in advance, and maintain it for one particular process. So some process can say, I'm going to need 5 megabytes a second guaranteed for the next 10 minutes, and it can actually make that guarantee happen. The real-time operating system that we looked at the other day does not actually use it. The one on the Zumwalt class destroyer, it actually uses it has its own file system like LinksFS or something like that. Anyway. Okay, that's good for this time. I want to start talking about the stuff in the textbook next time, which should be lots of fun. Oh yeah, and that project is due sometime or other. I don't remember when. I think it's due on Monday, and so don't forget about it and not do it. I'll probably check my email like Sunday night, just in case everybody's asking questions.
I have a project done and I keep forgetting to submit it.
Okay, well don't forget to submit it.
Yeah,
But it's a small enough class that if I don't see yours, I'll remind you instead of giving you a 0.
Okay.
I never used to do that when I had 100 people in the class.
Oh, also, I did